3, 2, 1.
मेरा कैमरा चालू नहीं था ना। हाँ ठीक है। हाँ, ठीक है। तो डेंसिटी फंक्शनल थियरी मेनली यूज होता है इलेक्ट्रॉनिक स्ट्रक्चर फाइंड करने के लिए इन डिफरेंट सॉलिड्स। तो ओके, तो इलेक्ट्रॉनिक स्ट्रक्चर क्या हुआ? इलेक्ट्रॉनिक क्या हुआ? कान क्यों बंद कर रहा है तो आपने?
अरे आवाज करता हूँ।
हाँ, इलेक्ट्रॉनिक स्ट्रक्चर फाइंड करने के लिए पहले अपने को एनर्जी वैल्यू पता होनी चाहिए फंक्शन ऑफ के, बट उसके लिए वी नीड अ वेव फंक्शन, राइट? To get the wave function, we have to solve the Schrodinger equation. And to solve the Schrodinger equation, we should know what is our system is, therefore our Hamiltonian. But the problem with this traditional approach is, for many particle, like for many particle system, this you cannot solve the Schrodinger equation because first of all, these are non-linear, and you have to solve all of them simultaneously because of the potential term. The potential term is dependent on each other. Okay, so we cannot solve the Schrodinger equation basically. So what can we do? So density functional theory basically bypasses this the first two problem, and then it directly calculates the energy from the Hamiltonian, which here we use density as our primary variable rather than a wave function. The main advantage of this is कि wave function जो है वो 3n coordinates का function है and s spin coordinates अगर magnetic properties को study करनी है, but density is just a function of three variables. So as I said कि ये हमारा system है, ठीक है, where your first term जो है that is the kinetic energy of any electrons. The second term is kinetic energy of nuclei. उसके बाद दोनों के potential terms and the potential term between electron and nuclei. So you see कि this is obviously very complicated और ये सारी information अपने को नहीं चाहिए. So we can drop some terms इसमें से. So the first term which we will drop is this, the kinetic energy of the nuclei, because both electron and nuclei, they both work on different time scale. So if I move the nuclei, the electron moves instantaneously. So for a given time frame, I can the electron will see nucleus as stationary. So that term is out, and the another term I can drop is the potential energy between the two nuclei. So if both the nuclei are same, like in a homogeneous system, and they all interact like exactly always the same everywhere, so we don't have to actually calculate that term if we want to know the electronic structure. Okay, so this is the total wave function for this complete Hamiltonian, which is obviously it is a function of small r, that means the coordinates of electrons, and the capital R, which is the coordinates of our nuclei. And this dropping of these two terms, or I can say not dropping, but separating this our Hamiltonian, two separate Hamiltonian, will allow me to write this write our wave function as product of two, where my first product is a wave function of electron, while my second wave function is the wave function of the nuclei. This separating the electronic part from the nuclear part is what I called Born-Oppenheimer approximation. So like this is the electronic part, and the other one is nuclear part, where you can see that in the nuclear part you can have this kinetic term, kinetic energy term, and potential term of the nuclei. So these two terms, they are only concerned with the nuclei part of the wave function. So so you can see that like h is my total wave function on the left hand side, uh, and then when I operate this uh, on my wave function, which has been I have already separated them out. The electronic part of the wave function will only act on psi of e, while the Hn, the nuclear part of the Hamiltonian, it will only act on x of r. So as I said, to know just the electronic structure, I don't have to worry about the h of n, the nuclear part of the Hamiltonian. So I can drop that out. So this is what I remain with. So this is basically is what my Schrodinger equation is. Okay, but this is still very difficult. This is still a many body Schrodinger equation. You still cannot solve this. So we have to uh, so we have to do further work on this to make it solvable. So, okay, so this is again recalling that this is my electronic Hamiltonian, and the Schrodinger equation is as written. And this is, as I said, this is still unsolvable. So, like I said, so this conventional approach is not working. Therefore, we will use a different approach from like since we have already know what is our Hamiltonian is. Now, from that Hamiltonian, we will use the density functional approach and then get the energies to get the electronic structure. So, okay, these are the two advantages which I've already mentioned. Yeah, also the you cannot measure the wave function, right? But you can always measure the charge density. So that is another advantage for density functional theory. So what we do, so when we cannot solve a Schrodinger equation, what is our first line of attack? Obviously, it is variational principle method. But in order to use the variational principle method, we have to guess a wave function beforehand. So this first was done by Hartree. So his guess wave function was just uh, uh so okay so his guess wave function was just product of single electron wave function. So he imagined all the electrons to be independent of each other, and this is what he started with to get the energies. So if I use this as my total wave function and then uh, do the variational principle, then this is the energy I get.
This is without spin, huh?
This is
Without spin.
without spin. There is no spin here. Okay. So okay, so there are two terms here. The first term, the H1 which I have written. Okay, yeah. So H1 I have defined. What is the H1 here? So H1 contains the kinetic term and the interaction term between the electron and the nucleus. And the second term, you can see that it is mod square of phi of k into 1 by r12 and mod psi of rk prime, sorry, phi k prime. So you so if so actually this is everything is in atomic units. There is also a charge E which has been taken as 1. So if you also have that, so E of mod square of psi is nothing but our charge density. And when you integrate out to whole space R, then you get the total charge. So the second term is just our Coulomb potential, like this, just Coulomb representation. Sorry, Coulomb potential which has been represented in terms of our wave function. While the first term, as I said, it contains the kinetic energy. So therefore, the first term has the kinetic energy term as well as the interaction term between the nucleus and electron. While the second term, as I said, it is considering the interaction between both, like how we do it in electrostats. So okay, so your K is the summation is okay. There is a prime on the summation, right? So that just prime, it means that K is not equal to K prime, which is if the K becomes equal to K prime, then uh, then it means that it is just interacting with itself, which is not possible. Now we will minimize this energy to get the Hartree equation, so that we know what are these single orbitals are, which has these energies. So, there are constraints here. We cannot just simply vary this single orbital wave function any way we want. So, okay, this is like we are like I said, I'm varying my single particle wave function one at a time here. So that is what it means, that del of phi I of R1 equal to 0 for I not equal to K. So for kth orbital is what I am varying, which you can see in the first equation. But the rest of them, they are not changed. So I vary one orbital. After that, I will vary the second orbital, and so on. So one at a time. And the
This variation is like the variation of action, right?
variation of
When we
action.
have a function,
Hmm.
we change the mode, and then I have action changes.
Yeah.
It is not like the usual variation which is not in the cat box, where you just make the thing, or is it the same?
You can treat it as the same, because like where in our usual variational method, you varied the parameter there with respect to the energy. But here the first orbital wave function itself can be treated as a parameter.
It's really
Hmm. But as I said, you cannot vary this however you want. You have to introduce this constraint that you are varying it, but the wave function is normalized, as well as it is orthogonal with other wave function. So using this constraint, you can solve this using Lagrangian undetermined multiplier method. So the first equation is your complete equation, which you have to vary, and after doing this variation, you get to this equation. Now this equation, since we have varied this energy with respect to only single orbital wave function, you can see this equation is now become a single body equation. The phi of k, which it is operating, so like the Hamiltonian is operating on phi of k, and on the right hand side you can see that it is given out an eigenvalue, and then you're getting the phi of k again.
but there is R1 cube, right? I can see R1 cube.
R1 cube, but
R1 cube.
that itself is an operator. Summing over integration of 5k prime of R2, the whole mod square by R1 R2. You see what is this? You are basically averaging over all the electrons. So you are summing, and then you have this probability 5k prime of R2 or the mod square. So that is the probability of R k primed electron, and then you are summing it over. So this is where the idea of mean field comes from. So essentially you are only looking at one particle, that is one electron, and all the other interaction is been dumped into this second term, which is just an average over all the field around the
This is like now this is like an external potential which is seen by R1.
yeah, right, just seen by phi of k.
Fine.
And in H1 you just have the kinetic term and the interaction with the nucleus. Interaction with the nucleus, as I said, is not much of important, because we have considered nucleus to be stationary. So it is there, but it is only acting as like we can say as an external potential just. Okay, so here the problem here is it is not yet complete because the wave function we start with was not antisymmetric, but we know that the electron uh, when we consider the more number of electrons, the total wave function should be antisymmetric. So 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 you have to improve on that, improve on this. So that is where Folk came. He suggested to use a new wave function, which is this Slater determinant wave function. And then using this wave function, we will now do the exact same process again. We will find out the energy, and then again we will vary it with a single orbital using same constraint, and then we will again get an equation which is we call a Hartree-Fock equation. Introducing antisymmetry to this has encoded a very significant property of the electron, which is the Pauli's exclusion principle. The Slater determinant, so you can see if let's say two electrons is in the same state, the determinants become zero. If you so the two rows will have the same entries, and then that wave function will be zero. Or even if you have two electrons at the same position, so the column will have the same entries, and then it will again be zero. So okay, so using this wave function, now we will do the same process again, and then this is the Hartree-Fock equation we get. You see the first two terms is the exactly same as the Hartree term, but there is an addition of new term here, which we call as exchange energy term. This exchange energy term is as it is says that this has came because when we exchange two electron, the parity flips. So that is the antisymmetry property of the electron. So from the antisymmetric property of electron, we have gotten this third term. That is why it is called the exchange term. So this term is like purely quantum mechanical. You cannot realize it as you realize this Coulomb term and then the other kinetic terms. This is purely a quantum mechanical phenomena, and and this is still not complete. So so you have gotten this kinetic term, the external potential which is inside this H1, the Coulomb term, the interaction between the electron, and then the exchange term which is happening because of the spin. Like so this PS it means so it is only valid. So this is only valid for parallel spins. So for the parallel spins, the electron will actually repel each other, but for the anti-parallel spin, they will attract.
Where
So that
did
is
we choose this parallel of antiparallel?
it comes from the derivation itself. So like as you solve it, it naturally comes in the mathematics.
Only parallel won't survive.
Hmm. So this summation will only apply if your k prime and k if they have parallel spins. So that is how, so from antisymmetry property, this is how the Pauli's exclusion principle enters uh, in in the Hartree-Fock equation, which was not there earlier in the Hartree.
You know, anti-symmetry in the spatial wave function forces the parallelism.
Yes.
Yeah.
So like okay, so this is the energy. Varying this energy, we have got the above equation. So like as I said, this is still not complete. There is still one extra term here, which is called a correlation energy term. So that is also a purely quantum mechanical phenomena. Like it tells like how the electron will dynamically vary its position when you move one electron. As I said that I'm wearing one orbital, one at a time. So when I'm moving one orbital in my variational case, all the other orbitals are static. Like this is what you call a frozen orbital approximation. So the cost of that approximation, now we have not gotten the correlation term in this. That is the main drawback of the Hartree fork. And in fact, we know so little about correlation energy. It is defined as exact energy minus the Hartree fork energy. That is the only definition we have for the correlation energy.
You good.
So this is why we have to because it has both. It has exchange energy as well as correlation energy. So this gives us uh, much better estimation of energies than Hartree and Hartree. Also, this is less computationally heavy than the Hartree fork because here now we are working with densities rather than wave functions. Okay, so yeah, so I think so. This is again I'm redefining everything here. This is the Hamiltonian which we are working with, where I've said that the interaction between the electron and nucleus is our external potential. Uh, and I have denoted each term with T, U, and V. So this is the notation which I am be using ahead. So that is why I have redefined it here again. And the corresponding energies is the just expectation of T term, U term, and V term. Okay. Yeah. So first of all, what is density in quantum mechanics, right? So the definition of the density is as given. So when we solve this, we get the following integral. In the integrand, you can see that the total wave function is just mod square, and then you sum it over all R2 to Rn except R because we need density as a function of R. So okay. So this is just a definition. Like this is the definition I'm working with for the density of our electron. Now I will write the external potential in terms of density because it was earlier it doesn't contain uh, any n there. So I have to rewrite my external potential operator in terms of density. So you can see like since my electrons are indistinguishable, so all this RIs they are all these all are reductant variables. Like I can choose what R1 and then operate my V external there, and then again choose my other R1 and then do it separately. I don't need the information of all RIs at once. गर्म हो रहा है भाई। वो सोच रहे हैं कि भाई सब लोग एक साथ कैसे ऑफलाइन चले गए। प्रैंक हो गया भाई ये तो। अरे नहीं नहीं, वो एंटीसिमेट्री की वजह से क्या हुआ कि एक हिडन इंटरेक्शन था बिटवीन द पैरेलल स्पिन, वो एक्सपोज हो गया। देयर इज नो इंटरेक्शन बिटवीन द एंटी पैरेलल स्पिन, दैट्स व्हाई दे कैन सिट टुगेदर, बट पैरेलल स्पिन कैन नॉट सिट टुगेदर बिकॉज ऑफ द इंटरेक्शन टर्म, सॉरी एक्सचेंज इंटरेक्शन टर्म।
आवाज नहीं आ रहा।
मेरा आवाज नहीं आ रहा? मेरे को तो यहाँ पे दिखा रहा है कि मैं बोल रहा हूँ।
आ रहा है आवाज हमारा प्रथम।
आ रहा है आवाज। कुछ भी बोल रहे भाई। मैं तो बोला है। एक काम करता भाई, मैं तुम्हारी हॉटस्पॉट पे रहता हूँ, ये लाइट का कुछ भरोसा है नहीं, ठीक है? बाकी तुम लोग स्विच कर लो। हाँ ठीक, क्या था ये? हाँ ये था। स्क्रीन शेयर है ना, नहीं है क्या? हम्म, हाँ ओके, so before we start using density rather than wave function, we have to first make sure that every charge density has its unique external potential. Because let's say we have 3-4 charge density, but they all map to same external potential. Or we have 3-4 external potential, but they all map to same charge density. Then it is not useful, right? Like every charge density should have a unique external potential. Then only we can solve it iteratively and then know that yes, this is our ground state. To prove this uniqueness of potential for for each charge densities. So the first theorem says that for density n of r, क्या आपको ज्वाइन किया या लीड किया? Okay, and vice versa, ठीक है? And the second theorem says that a universal function for the energy E of n in terms of density n of r can be defined valid for any external potential. For any particular V external, the exact ground state energy of the system is global minimum value of this functional, and the density on of n of r that minimize this functional is the exact ground state density. अब मैंने ये exactly read किया because these two theorems are very precise, so I don't want to add or subtract anything from this so that it can be misunderstood. But it just says that like every external density, there you have a unique mapping for your charge density. And the second theorem says that if there's n of e and then you see the global minima of this n of e, the corresponding n naught which you will get will indeed be ground state charge density. That is all these two theorems. Okay. क्या आवाज नहीं आ रहा?
नहीं आ रहा।
अच्छा अच्छा।
बोलो।
Yeah, so we have already written our V external in terms of charge density. Now this T of n and U of n, they together they are called as universal operators. or you can universal functional, you can say, because these two terms you will find them in all systems. You change the external potential, the system will be different, but the kinetic term and the electron-electron interaction term, they are same in all the systems. So this is our T. This is what we start with, and then my job is to write this now in terms of density. So again, like if we consider our Hartree wave function, we can rewrite the above equation as this, and then from Thomas Fermi approach, which is like very easy to see, like it is just you have this h cross square k square by 2, and from that you get the Fermi sphere, and then you divide it by by 2 pi by L, the whole cube, and that will be equivalent to the number of electrons. So from there you get this form that the T of n is basically it is uh, proportional to n of n raised to 5 by 3. Like, okay, I cannot say proportional to because there's integral sign, so that will change the power. But this is the form what we get for the T. So we have written T in terms of charge density. We have already written V external. Now we only left with U term, which is our electron-electron interaction. So electron-electron interaction, we will again borrow it from our Hartree theory. Like as I said, the Hartree theory. Okay, like have I written? Okay. So if you remember in Hartree theory, if I go back here, you can see the Hartree. This, yeah. So the second term, if you see this summation over k and k prime, inside you have this mod of phi of k and mod of phi of k prime. And as we have earlier defined what our charge density is, this summation with this k, this phi of k is nothing but our charge density, which is a function of r of 1, r1. Similarly, a charge density at r2. So let me just show you again. Okay, so yeah, so as I said that you remember there are two summations outside. मेरा cursor दिख रहा है क्या? हाँ, there are two summations outside. So with one summation will go inside, and then that will become r of n of r. N of r1 I have just written as n of r, and then with the r2 I have rewritten it as r prime. So both those summation will get absorbed to get you this n of r and n of r prime. So you have written, so we have written u in terms of density, okay, T in terms of density, and also the external potential. Everything is now known to us. All three terms we have known in terms of density. Yeah, this 1/2 factor is being multiplied so that we don't double count the interaction. Like the like uh, like electron 1 interacting with electron 2, but also electron 2 interacting with electron 1 is the same. Yeah, so that is what this half is about. Yeah, so okay, so this is where the jugaad comes in to try to fit in our exchange, uh, our exchange energy, and as well as our correlation energy. So you see here we have, I have, so this is my exact energy. Like the first term you see, T of n, U of n, V external of n, and this is my exact energy. And this T of this small subscript s, which means T simulated. Uh, this is the form that we have actually written in terms of n. So this is the form we know what this will look like in terms of n. That n of 5/3. which we get from Thomas Fermi approach. I have added subtracted this as well as my Hartree potential. I have also added subtracted this, and then I have just rewritten it like I have written this term ahead, then this term ahead. So basically, I'm picking the terms which I know how to write it in terms of density, and then the rest of the term I'm throwing all this in this one single term and calling it as exchange correlation energy. So now I know the first three terms, but I don't know the last term. Till now, density functional theory is an exact theory. It can give you the exact ground state energy. But the like you can see the big caveat here is that we should know what is this exchange correlation energy is, which we obviously don't. That is why we started with this theory first of all. So rest of the theory is just to approximate this last term. So okay, so but first this is the energy as we know. So we will again minimize it, but now we will minimize it with respect to our charge density, right? So okay, so first, so I will give you a little brief what is auxiliary systems are. So so let's say this is on the left hand side. I have a real system, all the particles are interacting with each other, and the energy is given by this written below, right? This is the exact energy. But the auxiliary system uh, is just electrons or let's say any particles which are not interacting, but the field which all of them they are collectively interacting has the same charge density as the real system is. So so rather than dealing with this many particle interaction, like all particle interacting with each other, and then knowing what the ground state charge density will be, I'll just say that okay, I have this particle, this fictitious particle that are moving around, which are not interacting with each other, but they are interacting with an effective field, which gives me the same charge density as my real system. So once I know what is this effective field is, which corresponds to my real system, I can get the same charge density as the real system. So again, my problem will be reduced to a one body problem. This is exactly like mean field, like every particle is interacting with a effective field, be effective, and you will get like n number of one particle equations, which you can solve them one by one, right? So this is the idea basically to like what this V effective will should be such that I get the same charge density as my real system. And this is, as I said, this is again the minimization problem which we have already did in Hartree and Hartree fog. Like what we did in Hartree fog. In Hartree fog, the equation which we get was the combination of the kinetic term, the external Coulomb term, and the exchange term. The Coulomb term, external potential, and the exchange term is my V effective, which I got there when I use my antisemitic wave function and then I minimize it. So that was my V effective there, which was written for my wave function. But here I need this in terms of electron density. So now I will, so this is why I will minimize it so that I should, I know, I like, so that I should, like, I will know what is that V effective is. So yeah, so like again minimization, again the same constraint, and then again using the Lagrange undetermined multiplier. This is the equation I get, and this is the Kohn-Sham equations. So So all the terms here, they are, huh? Once- so all the terms here, they are represented in terms of densities. So and the second term, the third term, and the fourth term. This is essentially what my V effective is, also known as Poncham potential. And you can clearly see this is again a single particle equation. We know how to solve this. So after doing this series of approximation, does this work? It works. It works really well. but this last term, this uh, exchange correlation term, we still don't know how to deal with this. So this has came from like minimizing my uh, exchange correlation energy varying with charge density, right? Now how to deal with this last term? So as I said, there are many approximation which I will discuss further. So, but before that, like how do you solve this, right? How do you solve Poncham equations? So you start with density, like you can start with any density. Like here you can see it is just a superposition of all the one particle wave function. You start with this density. You plug in that in the Poncham equation. You get single particle orbital. You again put that in here, and then you again get charge density, and then you just solve this iteratively. And you do this until the initial input charge density matches with the output charge density well enough. So that is your ground state charge density basically. But you can only do this when you know what is this last term is, which will uh, so this is the algorithm basically which I just explained. So okay, so like how to get this last term. So here the approximation starts. Like until this point, density proportional theory was exact, but because of this approximation, it is not. It becomes inexact. So the first approximation is I'll just briefly go through this. Okay, so I'll just this first approximation is called like local charge density approximation. I'll just explain qualitatively what it means. So you just uh, pick a point, and to calculate the exchange correlation term at that point, you assume that locally the charge density is constant. So by doing this, you get this exchange part. While for correlation part, you have to use uh, quantum Monte Carlo. Like there is no like functional representation for this correlation part. All you get is a numerical value for this term. But for exchange part, you just assume that locally the density is homogeneous, and then at each point you can calculate this exchange correlation energy. And then so this is the exchange correlation you get from LDA. And then there are more sophisticated approximation like GGA, where not just uh, you consider like the locally the charge density is homogeneous, but you also consider the gradient. Like it is also varying. So locally also the charge density is varying. So you here you can see now this integrand is a function of n of r as well as gradient of n of r. So even those minute variation you consider to get much better approximation. So so I have written here like the problem with LDA is that it estimate atomization energy to be very large. So So the problem of overbinding happens when you want to calculate the atomic energies. But for like solids like sodium, potassium, like this s orbital solids, that the electron is completely delocalized, LDA works pretty good. But for 3D transition metals, where the electron is not completely delocalized, it is localized to atoms, where there you have to consider also the gradient of uh, charge densities. So, so GGA can work in 3D transition metals and all that. But it doesn't stop here. Like there are much more sophisticated approximations. You have approximations like these hybrids where they take some part of the Hartree fock and then some part of DFT, which are like completely non-local approximation. So non-local means to calculate the energy density at one point, like energy density of exchange polarization at one point. You consider the charge density of all all over the space, and then do that for every point. Like how LDA was local, like to get the energy density at one point, you only consider the local behavior of the charge density, while GG was semi-local. You consider the local charge density and also the variation in that. You have much more advanced approximation, but obviously the computational cost increases as you use much and much mature approximations. So okay, yeah. So this is what essentially density functional theory, like what the mathematics of density functional theory is, which uh, is going in day-to-day calculation of for, to calculate our electronic structure and band gap energies and everything. Yeah. So thank you.